everyone. Can you hear me? Okay, well, we're just gonna start then. All right, so this is going to be the last week of this class. So yeah, don't like show up next week because there won't be anything next week. All the materials should stay up as long as the classroom still exists. I'm not sure like when the classroom does end up getting deleted, but if you do want to keep all the material, which I do suggest that you do, you can just download it right off the classroom. What else? I think that's, oh yeah, that's right. And if you ever want to like see the recordings of the classes or past classes, I'm pretty sure you can find everything, like all the videos just on the Alphademic YouTube channel. So you can just search for Alphademic on YouTube and it should pop up. I think there's also a link to it on the classroom stream as well. So everything that I went over is going to be available for your own use. So make use of it as you see fit. All right. So out of the way, this last class's topic is going to be combinatorics. And I think one thing you might notice is that there is a lot of overlap with stuff that I've talked about for the last few weeks. So something like permutations and combinations and the Binomial Theorem and maybe other stuff. But I guess the reason why I could say that is because, well, the reason why you'll see that there is some overlap with previous classes is because these like concepts or ideas are just extremely prevalent in multiple like areas of math. So it like kind of highlights how important it is to understand some of these because they can be applied to such a wide range of problems. All right, so the other way, I think that also means that I don't have to spend as much time going over all of the stuff in the lecture. I'll just like go through it quickly and I'll explain the new stuff like I usually do. All right. So combinatorics, as you'll see, is similar to probability, but you're not calculating probability. You're simply just doing the counting part of it, and it has a few different concepts. So first one is permutations and combinations, which I've used for the past few classes. So all of this should just be a refresher. And yeah, if you have any questions on permutations and combinations, please do ask. Otherwise, I'm just gonna move on from this section of the lecture notes. Okay, so I guess I'm gonna go on to distinguishable versus indistinguishable. So this should be a new topic, and can you hear me? It says that audio is not going through. All right, wait, can someone like tell me if they can hear me? I just got
yeah, we can hear you.
All right, just my internet is sometimes kind of suspect. So hopefully it's better now. The thing with distinguishability versus indistinguishability is that it really changes a problem if you aren't able to identify which of the two, I guess, ideas are used. So essentially you'll see that when you have indistinguishable objects or something like that, you use combinations, and distinguishable, you usually see permutations. But the main idea is that if you have something like you're putting like balls in boxes, it's just kind of a example, I guess. And essentially, if the boxes are indistinguishable, then that means that, and let's just say the balls are indistinguishable, then that means that the only thing that matters is the number of balls in each box. And see, if there are like 6 here, like there's 6 total, it's just an example. And like something like having 4 in one and 2 in the other is the same as having 2 in one and 4 in the other. So you can kind of think of it like an unordered pair would be if they're both indistinguishable. And then if only one of them is indistinguishable and the other is distinguishable. So if you have the 2 boxes are distinguishable, that means that they're different. So then essentially how you would treat that would be where the you're still only caring about the number of the balls in each box, but now this like 4 and 2 and this 2 and 4 are not the same because the boxes can be distinguished between. And the next case would be if both the balls and the boxes are distinguishable. And now for this one, then this would be like 2 to the 6th, because since each ball is distinguishable, we have to treat, we can't just like count the number of balls that are going into each box. You have to specifically identify which ball is going into which box. So then that means that you can kind of treat them separately. So then for each ball, each one can either go into the first box or the second box, and so on. So that's why it would be 2 to 6, because we have 6 balls and each one has 2 options. And the last one we didn't go over is if one is indistinguishable, the boxes are, and the balls are distinguishable. So now this one is kind of, as you could say, this one is slightly more annoying to deal with, because you still have to consider, now you have to consider like the orientations of the balls relative to each other. So that means is that you can, well, it's actually not that bad, but essentially what you can do is treat that the 2 boxes are distinguishable and then order it like such. So now they give you 2 to 6, and then you simply just divide by 2, because you'll kind of be overcounting each. Like you'll be kind of overcounting it twice, because the boxes will be flipped compared to when they're compared to when they're distinguishable, like your unordered pairs of boxes, or your ordered pairs of boxes now become unordered. Although I kind of glossed over it, the concept is, it's less like just remembering like a certain formula or how to just approach it every time. A lot of it is just using your own logic and this experience with, I guess, each kind of case. And when we do the problems, this idea will be quite a bit easier to understand. But I kind of want to highlight how these two, like distinguishability and indistinguishability, affect how it can affect like us, like the same problem, and change it into like a lot of different problems. All right. Next is, so next is stars and bars, and this one is probably the most basic way to order a group of indistinguishable objects into distinguishable boxes or sets. So what I mean by that is, let's see, you can probably just read the page here. It says you can kind of think of every object as a star and a bar as a divider of separating objects. So what does that mean? So if you see here from our example like this, you'll see a lot of problems can kind of devolve into a similar type of problem. So I'll give another example. Let's say we're going and buying 12 donuts from a shop, because yeah, and there are 3 flavors, and these 3 flavors are all different. And so how many ways can we order donuts so that we have 12? So essentially each donut can have 3 different flavors, but each donut is considered indistinguishable from all the other donuts besides its flavor. So essentially this would be like having indistinguishable donuts and distinguishable flavors. So like the stars and bars method would apply for this kind of case. And essentially what the method says is that we can let each object that's indistinguishable be like a star. So we can just like, I'll make the numbers smaller so it's easier to illustrate. Let's say we have 6 instead. All right, so let's say we have 6 stars and 3 flavors. So if you read here, there are going to be k stars and n-1 bars. So k equals 6 here, n equals 3. That means that we'll have n-1 or 2 bars. All right, so you can think of them as just 2 lines here. And so by stars and bars, the number of ways to divide these objects into the k groups is this expression right here, n plus k minus 1 choose k. All right, and I'm sure that you can write this algebraically using the formula for the combinations, but that's not how you show this is true. It's kind of just thinking about what this means. So if we let this n plus k minus 1, let's apply to this example. N plus k minus 1 equals to 8. 6 plus 3 minus 1 is 8, right? So let's say we have 8 places in a line. And so like each of these dashes are just like a place in line, right? So what this expression is describing is that from these 8 places, you're choosing k places. So k here is 2. So let's say we're choosing this k. Let's just say we're choosing that one and this one, sure, right? So then we can then just assume that these places are meant for the 2 bars, because there are equal number of bars as there are going to be like k, because I'm sorry, never mind. K, okay, it's the same thing, but k here is actually technically 6, but I don't know if I said this before, but we have this identity where n choose k equals to n minus k, n choose n minus k. And you can think of this like if you're choosing k objects from n, you can also choose the n minus k objects out of n that you're not going to choose. So that's why these are equal. And also if you plug it into the formula, all it does is switch the n minus k and k. So like this is the same because of the commutative property. So that's why I can just do that. So then this is also equal to n plus k minus 1, choose k minus 1, sorry, n minus 1. I just didn't write it like that because this way looks better. But either way, here's the idea. So either we're going to choose the 6 spots for the star or the 2 spots for the bars. It's all the same. And then the remaining ones we can just fill in, right? And now you can see that these bars divide the stars into 3 different sections, like section 1, section 2, section 3. And if we let flavor 1 just be equal to number in section 1, the number of flavor 2 is equal to number in section 2, and the flavor of 3 is equal to number in section 3. And essentially what we're creating here is a bijection, or a one-to-one correspondence between a certain way of ordering these shapes with some way of ordering the donuts, in that just some way of finding of putting like numbers, just like finding an arrangement, I guess you could say, of numbers of each flavor that you're getting. And so I hope that you can see that this method does actually get every possible case. Because, for example, if you're wondering why, I don't know if you're wondering this, but if you're wondering how you can get a case where there's 0 in the flavors, so like if you have you get none of one flavor, then you can just have like 2 bars next to each other, and so like the first 2 would be 1, the section 2 would have nothing, and section 3 would have 4. So either way, that's the main idea behind this. And this method is a very, very powerful tool that you should be using for a lot of these combinatorics problems. And yeah, all right. And this example problem is essentially what I just went over here. All I did was change the 12 to a 6. So yeah, just I commit that to memory. All right. Next is about sets. I'm actually going to talk about sets a bit later, since it works better with principle of inclusion and exclusion. So I'm just going to put that off for after I do the binomial theorem and the stuff on the next page as well. So binomial theorem is something that we went over last class. And so if you weren't here, if you don't remember, it's written like this. And I guess the explanation of why it makes sense, I guess if you don't know it, I don't really want to explain it again. Also don't, because I kind of have to be efficient with my time here. So you can either just look at last class's recording where I explain it, or you can look it up, or you can try to figure it out on your own. I show you that why it makes intuitive sense is not very hard to grasp if you understand the meaning of the n choose k in this context. All right, so I'm going to go on from that and go to Pascal's triangle. And this is a really, really cool, in my opinion, a representation of combinatorics. So essentially in Pascal's triangle, we start off with the number 1 and 1 and 1 here, and then every number else or after in the next row is just the sum of the 2 numbers diagonally above it, and like the 2 end numbers are always going to be 1. So you can see like 1 plus 2 equals to 3, 1 plus 3 equals to 4, 4 plus 6 equals to 10, 10 plus 10 is 20, 20 plus 15 is 35, etc. So you can kind of like manufacture the table on your own. And the cool part about it is that each row here corresponds to unique, so let's just call these rows 0, 1, 2, 3, 4, right? The cool part about this is that for each row, the numbers are going to be in order. Like if the row is n choose 0, n choose 1, n choose 2, all the way to n choose n. So if you take any row, let's say we take the largest row in this diagram, 7, n choose 0, 7 choose 0 is 1, 7 choose 1 is 7, 7 choose 2 is 21, 7 choose 3 is 35, choose 4 is 35, and so on. This is all true. And essentially for any row, actually, this will be the case. I believe the proof of this will not be shared. I guess you can actually do this algebraically, I believe. So I'll just kind of give an overview of it. So if we like write it algebraically, the way that Pascal's triangle works is that n choose k equals to like n minus 1 choose k plus n minus 1 choose k minus 1. Right. So I'll give you an example. This is 7 choose 5. This is over here 6 choose 4. Over here, this is 6 choose 5. Right. So these three numbers can kind of be plugged into here, and you'll get that this is just like a general way to write this. And since I said before that that's how the each row is generated by adding the two consecutive terms to get one like beneath it. This describes every of the interactions, right? And essentially, if you do end up writing the algebraic versions, so like this is n factorial over n minus k factorial times k factorial, and so on, right? So each of them has this factorial version, and if you like combined these two like fractions that you end up getting for the factorials, and if you do combine it, you will end up getting this. I know I didn't like physically show it, but if you're interested, you can actually try this yourself. I think it's good exercise, and you'll see that this is just going to be true straight up. And so what that means is that you can just use induction, I guess. Probably not you don't really need formal induction, but just the concept of it. Like if this thing holds for any value of n, then since the values of the row before are all the combinatorial values, then the next row is going to be the same as well. So that's just so like the point of that was just a way to visualize this row. And I guess another reason why I showed like Pascal's triangle here is for the hockey stick identity. This is slightly more advanced. You might not see it. You might not see it like in the AMC 10, but this definitely does show up later. So what this says is that the sum of I choose R from I equals R to n equals to n plus 1 choose R plus 1. So if I use numbers, this would be saying something like 2 choose 2 plus 3 choose 2 plus 4 choose 2 plus all the way to any number, let's say 11 choose 2. This is going to be equal to 12 choose 3. And yeah, like this, it's kind of cool that you can have just all of like these combinatorial expressions that don't seem like they should add up to just a neat number, and it just does. And as I wrote here, this is my favorite corollary because you can just prove this directly from looking at Pascal's triangle. And I'm just going to illustrate this here. So essentially, we can like locate all of these points on the triangle. They're like, let's say 2 choose 2, 3 choose 2, 4 choose 2, and so on. And obviously, the triangle doesn't go all the way up to 11, but let's say we stop here at 5. So let's say we're only going up to 5 choose 2, right? So then by the hockey stick identity, the sum of all of these terms going down this way is just going to be equal to this last term, 35. So like essentially going down a diagonal, and then once you reach the last one, you'd be going one down to the right. So it's there. And you can verify this 1, 3, 6, 10, 15, they do up to 35. And I guess the reason why this works is because of the property of Pascal's triangle, or multiple ones, that this next term is always going to be 1 because we have to start at R choose R. So essentially we can move this 1 down to the next one. So the sum of like the diagonal is equal to, if we just replace the first one with the 1 next to the 3. But now this 1 and 3, they add to 4 because of, again, the Pascal's triangle construction. And this 4 and 6, like on the next row, goes to 10 right here. And this 10 and the 10 goes to the 20, and the 20 and 15 goes down, right down to 35. So essentially, you can see that this will work for any kind of like hockey stick that you draw on the triangle, which is why it's given that name. So yeah, and it does go the other way as well. So you can have hockey sticks that go like reversed, but it's kind of all the same thing. So that's why I'm only showing this one. It's a more standard version. All right, so I guess what I did all of this. Maybe not like it won't be like the most useful for competition math, but I think it does give you a good, not good, but like it does give you, I think, a good image or some kind of introduction into just how deep this combinatorics can actually go. All right. And so actually the last one that I forgot to mention here is the sum of each row is 2 to the power of that row number. So yeah, if we do clear out this triangle a little bit, you can see that the sum of the row 1 is going to be 1. The sum is 2, this is 4, this is 8, this is 16, this is 32, 54, 128, and so on. So it's like 2 to 0, 2 to 1. And this fact is actually pretty useful. So I guess you can show that this is true for any row because each row is just going to be twice of the one before it because it includes 2 copies when you use to like add them to the next row. So like the one in the previous row appears in each of the 2 numbers below it, and same for every number in the row above it. So that's why it's always exactly 2 times. And so that's why we can guarantee that the sum is always going to be 2 to some power. And from that, we can easily show that this is true. The sum from n choose 0 all the way to n choose n is equal to 2 to the n for any value of n. So this is actually an important fact to remember, and it's actually useful regardless. All right, and lastly, back to sets. All you really know is just a little bit of set notation. So if you see a U, it means a union, or like the number of total elements in both sets. So if you have like a set with elements A and B, and a set with elements of like A, B, and C, the union is just, the union of these like 2 sets is just A, B, C. And this intersection symbol, or the upside down U, the intersection would be A, B. So intersection just means any common elements between 2 sets. And a set is just a non-ordered collection of elements, I guess. And usually these elements are going to be distinct. And the reason why I just defined it is because of this principle of inclusion and exclusion. And this is also a very important thing to remember. And it kind of states that this absolute value sign represents cardinality. The cardinality of the union of 2 sets is equal to the sum of the cardinalities of 2 sets minus the intersection. So if you apply the example here, this would be like 3 plus 2 minus 2, or 3. And union does have 3 elements. And you can kind of see this using a Venn diagram where you would have this, where you'd be like adding the circle, you'd be adding this circle, and you'd be subtracting the middle part because you counted twice when you added the 2 circles. And the same applies to this one. I'm not going to read out because it's kind of long, but it's for like 3 different sets. Then each region in the Venn diagram can be described by one of these expressions. And yeah, if you do verify it, like by counting out how many times each region is added and subtracted, you'll see that it should be all 1. And this one especially is tested very often, so be sure to remember it. It's also, a lot of it is just intuition too. All right, so that's it for the I guess notes section. And if you do have any questions, you can ask anytime. But I think we're just gonna otherwise just go down to the problems. So yeah, for the problems, I think we're just gonna start from the beginning. I don't see any there. Start, no. All right. This first one I think is a really just a simple problem that you'll see. 2013 number 11, and you're essentially selecting 2 people from a committee, and sorry, you're selecting 2 people from a group of some number, and you want to find another way to select 3 people, and you're given that there are 10 ways to select 2 people, and it's possible for them to serve on both committees. How many different ways can 2-person plan can be selected? And this is simply just, you know, n choose 2 equals to 10. And you want to find n choose 3. And basically, you can find that this is just 5. This is just some, I guess you can just see it. If not, you could try to solve for it. But I just want to remember, you do try to memorize the common, or maybe not memorize, but like at least be very familiar with the values of the combinations for small numbers. So either way, you can find this is 5, and 5 choose 3 is equal to 5 choose 2. So this is just 10. So all this problem really does is just introduce the concept of using these combinations. All right. Next, this is just counting problem. 10 chairs are evenly spaced around a round table, and numbered clockwise 1 through 5. 5 married couples are to sit in the chairs with man and woman alternating, and no one is to sit either next to or across from his or her spouse. How many seating arrangements are possible? All right. So I guess the idea here is this kind of problem, there's no formula or just a simple combination that you can do to solve it. So I think it was good to just visualize it. So if we have probably looks like this. All right, the tables, if we label them 1 through 10, and yeah, the seats are labeled 1 through 10. See that like 1 is across from 6, 2 is across from 7, 3 is across from 8, 4 is across from 9, and 5 is across from 10. All right, how many seating are possible? So in problems like this where there is a fixed order here, right? Each chair is labeled. That means that like the chairs themselves are not indistinguishable. They're distinguishable chairs. And since there really aren't any other constraints, we can kind of like step through the problem in a sense. So, and what I mean by that is just, all right, since everyone is like different from each other, we can just choose any person. So let's say we choose a seat for 1 person, like to start off with. So like if we take 1 person, and this is going to be a unique person, obviously. So let's say there's some guy, M1, okay? He's going to be like the first person, and he just happens to sit at seat 1. And essentially we can just multiply anything that we find for this case by 10, as where like if he sits at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, it's going to be rotational symmetry. So that's why we can just consider this one case and multiply by 10, since all the cases are going to have the same values, right? And so now we can either place his spouse, or we can place another man. Essentially, we should be placing another person, another man, because that one has less constraints, which means that you don't have to worry about more cases to deal with. So like with that logic, you can go and you can just go ahead and just place all the rest of the men like in their seats. And you can just do this because, well, there's currently no constraints that says that you can't, right? And essentially, the reason why we did this is because now that all like the men are placed, there's going to be a lot more constraints, so less cases to deal with for the woman. Right. So if we take, let's say, the spouse of the first man, and they can't sit at 6, 2, or 10 because they're adjacent or across, that means they must either be in 4 or in 8. Right. So let's just say they're in 4. And note that there are 2 options here for where they could have been, right? So now the claim here is that after we place this first woman, all the rest of them are going to be fixed. Or what I mean by that is, after I place them, no other woman has a choice in where they can sit. And I guess you can kind of think of this because wherever this first woman is placed, they're going to be in a seat across from some other man, right? And so let's say the spouse of this man in seat 9, they can't sit in 8, they can't sit in 10, and they also can't sit in 4 because there's already another woman in there. So they must either be in 6 or in 2, right? And I'm missing something here. Sorry, give me a second to think. All right, let's start again here. Where was that? We said that woman 1 is in 4, and so that means that this spouse of the man 5 has to be in either 6 or in 2. Oh wait, yeah, no, that was kind of implied already. So let's choose a different one. So let's say we take let's take the spouse of the woman in of the guy in seat 7. Okay, they can't be in 2, they can't be in 8, and they can't be in 6, and they also can't be in 4 because that's occupied. So that means that they have to be in the seat 10. And essentially, you can kind of use this same logic that, but you can like eliminate 3 or 4 or something seats as options for every woman subsequently. So that would be why there would just only be 2 ways to seat all of the women, just from this first decision by the first woman, right? So then all this becomes is just 10 times 4 factorial times 2, because there are 10 ways for the first guy to sit, 4 factorial for the rest of the men to sit, and then 2 ways for the rest of the men, and that's equal to 480, and that's it. I guess with this problem, it's mainly just finding, I guess, a way to circumvent any kind of difficult casework and just look for easier tricks to solve it, I guess. This is just one of those problems where you can't rely on any set formula. You have to just kind of think for yourself. Yeah. All right, so next is this problem. It's actually mislabeled on the sheet. It should be 2008, not 2010. So yeah, that's just if you are going to be looking them up later on. And so if you read it, it says the two sets are chosen so the union is S and the intersection is exactly two elements. How many ways can this be done? So this doesn't use the principle of inclusion and exclusion, but it does kind of test you on intersection and union. All right, so first thing we should do is identify which two elements are going to be in the intersection, because that is the I guess the easiest part of the problem to kind of fix. All right, and they're going to be 5 choose 2 ways of deciding which elements are in the intersection. Since there are 5 elements, you choose 2 of them. 5 choose 2. All right, and this is equal to 10. And next, we're going to be left with 3 elements. So if we assume A and B are going to be the 2 in the intersection, that must mean that the 3 elements C, D, and E are going to be split into the 2 subsets, right? And since the two like have a union is S, that means that C, D, and E, each of them must appear in one of the sets, but none of them can appear in both. And they can appear in both because if they do, that means that they're also in the intersection, which kind of nullifies the first point. So that means each of them can only be in one of the containers, I guess you would say. And so each of them has 2 options for the container they're in. So there's 2 cubed equals to 8 ways of putting them in a set. But since the order of the subsets does not matter, you have to divide by 2 to get 4. Because each like pair, we have like for example CD and E, would have a corresponding pair with like E and CD, right? They're just in different order. Since each of them is paired up, we just divide by 2 to get rid of the pair or the overcount, and we're left with 4. And now we just multiply, since that's all the problem it has, and you get 40. That's it. All right, so with this problem, it's more like just being careful with the definitions of union and intersection with the sets. All right, so next we have this one. 17 pieces of candy are to be distributed among 3 bags. The red bag, blue bag must each receive at least 1 piece, and the white bag may remain empty. How many arrangements are possible? All right, so this one is not principal exclusion again, but it is, I think, a pretty interesting, just straight up counting problem. So since we have 7 distinct pieces of candy and 3 distinct bags, right? The total number of ways to just like put them in any bag is 3 to 7, right? So this is like our total number of possible spreads of the candy, right? But of course we have constraints, and that says the red and blue bag must receive 1 piece at least, and the white bag can be empty, right? So that must mean that we have to consider the cases where, and subtract the cases where the red bag and the blue bag do not have at least 1 piece of candy. So that would be subtracting the number of ways we have 2 bags. So we're only the blue bag and the white bag have candy, and the red bag doesn't. That would be 2 to 7, and two bags again for the red and white this time. 2 to 7th again. However, when we subtract out this, we kind of subtract twice the case where the white bag is all the candy. So then we'd have to like add back that 1 case because we kind of like subtracted it twice. So we have to add it back, right? So like it's only subtracted once. Okay, So this should just be the expression. Then you have like 2.87 minus 128 minus 128 plus 1, as is equal to 1932, and that's it. All right, so I said before this didn't use principle of inclusion and exclusion, but it technically does, and I guess I'll just show where it uses it, and it's really just in this last part right here. So, like if you consider the set of this is just like an expression of the first version here, where this first set would be just the 2 to the 7th, where the blue and white are the only ones that have candy in it. So that would be like, I'll just say it's A. B would be the one with just the red and white. And this intersection of A and B is when the two, when there's only candy in the white bag. So since we like only actually want the union of A and B, or like the total number of cases in which like the constraint isn't met, that's why we have to like subtract off the intersection. So that's kind of why I did this adding back 1 here. So yeah, that's kind of the explanation for why we have this kind of expression. Right. Okay. So we have 4 problems now. All right, I'm going to skip this problem simply because I think it kind of takes just say it's kind of like a casework problem. You can try it on your own, where it's kind of tedious, and yeah, it doesn't like it takes a bit of time. It's not very hard. It's just tedious. So that's why I'm skipping it, and it's because also these next 2 problems have, I think, more important concepts I want to go over. So yeah. So this one, there are 20 students participating in an after-school program, offering classes in yoga, bridge, and painting, and every student must take at least 1 of the 3 classes, but can take 2 or all 3, and we have some values, right? How many students are taking all 3 classes? And I want to do this problem because this is almost just an exact, or not exact, like this is exactly what you would expect a problem that utilized this principle of inclusion and exclusion for 3 sets to be. And because we can kind of see that, that like the 3 sets are just the number of people in yoga, bridge, and painting, right? So if I let them be A, B, and C, A is yoga, B is the bridge, and C is painting, we can kind of just plug into the principle of inclusion and exclusion. So 20 should be on the left side because it's a union of all 3 of these. Like they're all the students in the program. And again, since not again, but like since all of them, at least one of them takes 3 classes, sorry, they take at least 1 or 3 classes, that means they all have to be included in it. So that's why this is 20. Right. So now 10 students taking yoga, that just means this is the A term. This is 10. And 13 taking bridge, so this is the, you can say the B term. 9 taking painting, right? So this is the C term. Then there are 9 students taking at least 2 classes, right? So does that mean there must be like X taking all 3, and 9 minus X taking 2 of 3, right? Since saying that there are 9 students taking at least 2 classes, that means the number of people taking 3 classes, people taking 2 classes, they have to add up to 9, right? And the reason why I split it up like this is because if we go up to the principle of inclusion and exclusion, you'll see that all three of the ones with intersection of two classes, they all have a minus sign, while this last term has a plus sign. And so that's why we kind of have to make that distinction. And so that's why we split it up into x and I minus x. And since we have like that, we can just plug it into the equation. This is going to be the intersection of like two sets, and then plus x, and this is the intersection of all three. Right? And so we have everything. So now all I can do is just solve the equation. Yeah. All right. I don't actually know the values too. Let's see. All right, did I do something wrong? I don't think this goes to a whole number. Oh wait, I see. Okay. The reason why this was wrong was because, well, I made a mistake, obviously. But what I forgot was that the sum of the intersections of the two class of like this negative term. So this had to multiply this 9 minus x by 2. This is because each of the each person is counted twice here, because each person like taking one of the classes is counted in the intersection of A and B. And also, wait. Yeah, I think that's it. Actually, no, that's not it. Okay, I'll get back to you when I look at this after. But the method should be somewhat similar to that. Okay, well, okay, well, I guess we're just going to move on from that. Something must have went wrong, and I guess I'll post something about this on Classroom After Class. So just be on the lookout for that. Okay, well, next would be this problem. All positive integer monotonous if it's a one-digit number or its digits one read from left to right, from either strictly increasing, strictly decreasing sequence. For example, 3. Well, these are just numbers. How many monotonous positive integers are there? All right, and I want to go over this problem because it's kind of like there's a way to like connect a lot of these strictly decreasing or strictly increasing integers with combinatorics. So essentially, since these numbers are strictly increasing or decreasing, we can just choose some number of digits k from 10. And this is because if we take a strictly decreasing sequence, any k numbers, so say we just choose numbers 1 through 9, any like combination that we choose out of the 10 digits, we can just order them in decreasing order, and that corresponds to exactly one number. So that's why for a strictly decreasing sequence, we can simply just take 10 choose 1 plus 10 choose 2 plus all the way to 10 choose 10. But we have to subtract 1 because this 10 choose 1 here can include 0. And so this would be like 2 to 10 minus 2. And then for like a strictly increasing sequence, we can't choose 0 because that would always be like a leading 0. So we only actually have 9 digits to choose from. And so this would be like 9 choose 1 plus all the way to 9 choose 9. And this is the 2 to 9 minus 1. And note that we don't have the x subtraction extra 1 because 0 isn't a possibility to be chosen. So no one-digit number we're going to get is going to be 0. So then you simply just add these. So you get 1, 5, 3, 30. All right. So that was like the main idea here. So you can just relate the digits in each number to you can relate the digits in each number to the just to the number of such numbers there are. So yeah, in this last problem, if you read it, 3 brother-sister pairs from 2 different families. I'm sorry, 3 different families. You take a trip and they have 2 rows, so 3 seeds in each row. And yeah, here are the constraints. So essentially, the main realization here is that each row has to have the one person from each family. And this is because if we don't, that must mean one row has somebody like, so here the same letter means same family. One row has to have like 2 from the same family. So that would mean like the next row would have to look like this. Like then these 2 people will be like not satisfying the seating arrangement. And then obviously if we don't have that, then these 2 will be next to each other. So like with that, it's easy to see that there has to be 3 unique families in each row. Then from there, there are going to be 3 factorial, so the number of ways you can order the A, B, and C, times 2 cubed for the number of ways that you can have like either the brother or the sister from the family, and then times 2 because after you have chosen the 3 spots for A, B, and C, then there are like 2 spots for like the A, I guess you could say, and then after that the rest is fixed. So then that's just times 2, and then that's just 96. So I kind of just rushed through this problem, but essentially this is another just typical accounting problem where you kind of have to analyze the problem and then from there split it into the smaller problems where that you can have like kind of linear logical thinking. All right. Okay, so that should be it for this class. If you have any questions, you can just ask them now. Yeah. Oh, by the way, before you leave, I think, okay, never mind, you can leave. I'll talk about it. I just, yeah. All right, yeah, you guys can go. I'll be posting it on the classroom later. But yeah, after this, there won't be any more classes. So hope you've learned something.